Hello, everyone, and thank you for coming along. So, as my probably not totally visible title here says, I'm going to be talking about perfectoid fields today. Um, so first, whenever you want to talk about any kind of object, you probably should define what it is. Actually, I just remembered I should probably set some more light here because it's slowly getting dark around here. All right, so we are going to start with the definition. So the first definition is, before we get to perfectoid fields proper, we have to define what evaluation is. So let K be a field, evaluation on K is a map denoted with like an absolute value from K to non-negative real numbers, such that, first of all, it satisfies the property that x is equal to 0 if and only if, sorry, the valuation of x is equal to 0 if and only if x is equal to 0. The second condition is that it is multiplicative, so valuation of AB is valuation of A times the valuation of B. And the third condition is that the valuation of A plus B is less than or equal to, and this might be a bit of a surprise to those of you who have seen NORs before, I am going to demand that this is at most equal to the absolute value of A, and or the valuation of A, valuation of B, and the maximum of those things. So more properly, this valuation should be called something like a non-Archimedean absolute value. Non-Archimedean referring to this condition here, which is a strengthened version of the triangle inequality, because this is always then smaller than the sum of those two. But we demand a stronger condition on the valuation of the sum. Okay, and those are going to be main players in our discussion. So for some examples, the simplest examples are given by Q, where unfortunately, because of this strong condition, the normal absolute value is not a valuation. But for any, so K equal to Q, and for any P a prime, we define the absolute value as follows. We define it by the absolute value of 0 being 0. I will denote with index P. And any other rational number can be written as P to the power of n times A over B, where n is an integer and A, B not divisible by P. So by unique factorization, any rational number can be written in this way. And we define this valuation to be P to the power of minus n in this case. I will not be checking those conditions. They are pretty easy if you know something about arithmetic of primes. So basically, for example, the third condition here comes down to just a certain statement about divisibility of numbers. So it's not hard. Another example, and if we have those rational numbers, then we can form what is called the completion of this field under this absolute value. So whenever we have a valuation like this, or even with this weaker condition, we can define a metric by saying that the distance from x to y is equal to the valuation of the difference, x minus y. You can check that. Shouldn't n be in Z plus in particular? The answer is no, because I am allowing rational numbers. So for example, if I have 1 over p, then this is going to be p to the power of minus 1 times 1 over 1. So this is an example with a negative exponent. If I was working with integers instead of all the rational numbers, then it will be non-negative. Not necessarily positive, but also non-negative. Okay. So this is going to be a metric, even something called ultrametric because of the stronger conditions. And because of this, we can consider completions of fields or just like completions of metric spaces. I will not get into technical details. If you don't know what completions are, you should be fine if you just hand wave over something. In the particular case of the p-adic valuation, the completion is going to be the field k equal to the p-adic numbers. And we denote, and this field can be written as a field whose elements are sums. Maybe I should write it explicitly. A minus n p2 minus n plus a minus n plus 1 p2 minus n plus 1 plus blah, 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 where each of those a minus n and so on is a digit, p-adic digit. So ai belongs to the set 0, 1, p minus 1, and n is some integer. So I mostly wrote the minus n here just to emphasize that this exponent here can be negative. And if we call this guy here x, then if a minus n is not 0, then absolute value of x, or the valuation of x, is going to be exactly p to the power of n. So for example, if it had started at p squared, then this p-adic valuation would be p to the power of minus 2. Sorry, this should be capital N. And of course, valuation of 0 is 0. All right. So this was the first example. Another example which will be useful later is something called the field of formal Laurent series, which is denoted by k equal to f double bracket t. This is basically a generalization of polynomials. So any x in this field k can be written as an again a sum like this, so a minus n t2 minus n plus a minus n plus 1 t2 minus n plus 1 plus blah blah, where this times all of those coefficients a minus n are in this field f. So f is some fixed field. We don't particularly care what exactly it is, and we consider arbitrary infinite sums like this. And those are basically treated like polynomials. So when we want to multiply them, then basically we group terms with the same exponent of t, and then see what the sum of products of those coefficients is. All right. So after those examples, we have just one more quick auxiliary definition, namely O of k. If k is any field with valuation, then O of k we define to be the set of elements in k such that evaluation of x is at most equal to 1. This is called the ring of integers, or the evaluation ring. Of k. We have a question, why don't I consider the case where a minus n isn't 0 for large n? So I'm not sure if I understood the question correctly, but whenever we have any non-zero element like this, then one of those coefficients is going to be non-zero. And we can always write this element. We can basically just ignore the first few terms and then just say that a minus n plus 1 in this case. Oh, in this case? So is the question why we don't allow things to go infinitely in the other direction? If that's the case, then the problem is that in that case, it is not obvious how we would define products of such things. For instance, consider element x, which would be 1 plus t squared plus blah, 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 and y to be 1 plus t inverse plus t minus 2 plus blah, blah, blah. If we wanted to compute x times y, then what would be the coefficients of t to the power of 0? Well, we have 1 times 1 plus 1 times 1 plus 1 times 1, and so on. So it would be an infinite sum. So, and this is something we do not want to allow in this algebraic ring like this. There are certain rings, and namely Tate algebras and similar things, where you do allow coefficients to go terms to also go infinitely in the other direction. But then you also have conditions like the norms of those elements in some suitable norm have to go to 0. So in here, we do not allow this because we do not want any infinite sums like we would have here. But there are indeed contexts where we could allow that, but we have to be careful at any rate. All right, so I have written this O of k here. This is called the ring of integers or the valuation ring of k, this filled with valuation. And it's indeed easy to see that this is a ring. If you have heard the term valuation ring before, it has a proper definition in algebra. It is indeed satisfied here. And yeah, this is kind of like, and for example, in the case of k equal to qp, we have O of k is equal to zp. And this is the set of those sums which start with a0. So a0 plus a1p plus a2p squared, plus, and so on, where those can now be 0. If we take k to be f double bracket t, then O of k is f double square bracket t. And those are going to be the formal power series. So a0 plus a1t plus a2t squared plus, and so on. So hopefully you are noticing some similarities in here. Getting the similarity between those rings in a formal manner is actually the main goal of the theory of perfectoid fields. And I will get back to this a bit later. But now comes the moment that everyone was waiting for, namely I am about to define what a perfectoid field is. Okay, so definition. A perfectoid field is a field with field k with valuation it feels almost like the relation is like the one between the ring and a string of integers. So in this case, it's actually a bit more complicated. I'll go back here for a second. The problem is that the way we define the structure on those rings is actually quite different. So here we actually have the algebra here is pretty much like it is for arbitrary polynomials. So just treating those as coefficients and, as I said, grouping and whatnot. While in here, we have to care about how we are. When we add terms, we have to care about carrying. So, for example, if we took x equal to 1 and y equal to p minus 1, then if we add them, then the sum is going to be x plus y is going to be, the first term is 0, but then, oh, you cannot see that, sorry, it's going to be 0, but we also get a term in the higher degree, p. So this is something which couldn't happen in the formal power series ring. And this is what, because we couldn't have two like constant polynomials which add up to something non-constant. We have a question about we care about convergence. The answer is no. So the name formal in the formal power series is that it's precisely that we do not care about those series actually define converging on some ring and defining any kind of function or anything like that. We just allow any infinite series which goes to infinity like that. All right, so perfectoid field. So this is a field with valuation which satisfies a bunch of properties. So the first property is so such that first property K is complete with respect to this valuation. Again, if you don't know what complete means, then don't worry about that. You can kind of just put this condition in the brackets. It's necessary there for some things to be true, for most of the things to be true, but for motivation, which is what I'm going to do, this is not particularly important. Second condition is that the image of this valuation is not discrete in r greater than 0. This will hopefully get a bit clearer when I get to a non-example below. And the third condition, the one from which the perfectness in Perfectoid is derived, is that if we consider the map OK divided by the ideal generated by P to O of K divided by ideal generated by P, which takes x, any x to its pth power, this map is surjective. So there you have it. I think the accumulation, yes. So this is something that was actually pointed out to me yesterday, or maybe the day before, on Discord, that we actually always will have a single accumulation point. But again, you will see that in an example. And here you may be also wondering, what the hell is this prime P? The answer is that it is some prime, but we can be a little more specific, where P is such that the norm of P is strictly less than 1. In particular, we allow the case where P is equal to 0, so that the perfectoid field itself is of characteristic 0. Yeah, and you can show that this prime is complete. This prime is unique. Yes, so the valuations induce topologies. Yes, so as I mentioned earlier, valuation always induces a metric. And using this metric, we do consider perfectoid fields to be topological fields, or even norm fields in that case. And yes, when I say complete with respect to the valuation, I mean with respect to the metric induced by this valuation. So this is a bit of kind of notational abuse. Okay, on to first of all non-examples. So examples. Uh, so the first non-example is going to be QP itself. Okay, so this field is complete, so we don't worry about that. The third condition. So what does the third condition say? O of k is uh, the ring of p-adic integers, and O of k divided by the divided by p is isomorphic to fp, the finite field with p elements. This is the same as just z divided by p times z. Okay, and this condition on surjectivity here is actually satisfied because every element is its own p power by Fermat's little theorem. But the second condition is not satisfied. So if we look at image of this p-adic valuation, this is going to be, I'm going to draw it. Here is 0, because this is the image of 0. And here somewhere we have 1, here somewhere we have p, here somewhere we have p squared. And we are going to have p inverse, and we are going to have norms of all those elements going here in the to infinity and here tending to 0. So we will always have this accumulation point at 0, but you can show the image of the valuation is going to be a multiplicative subgroup of positive reals. So if it is non-discrete at any point, that it is if it is discrete at any point, that this is discrete everywhere. So this is something we exclude from the definition, because the motivation for perfectoid fields is that they, in a suitable sense, are fields which have a lot of p powers, in which a lot of elements are p powers, rather, I should say. So, and both of those conditions are here to make that precise. So these conditions means that kind of at the level of the residue field, we have a lot of p fruits, which here is kind of trivially satisfied. But this is not the case at the level of the norm, because this is where the set of here norms is very sparse. So one way to salvage this is actually to extend the field of p-adic numbers to a field which I will denote by qp, adjoint p to 1 over p to the power of infinity. So what this means is that we take this field qp and we adjoin the p to the k root of p for all k in n. So explicitly, the elements of this field can be written as sums of from a, from say I equal to 0 to infinity, of some ai, p to the power of ei, where now each ai is still a digit. So this is from 0 to p minus 1. But those exponents now, and including 0, doesn't matter because p is already in the field. But yes, for future reference, I always take 0 to be an element of n, but I don't think it will matter for this talk. Where was I? Yes. So, and those exponents, they can be now rational numbers. So ei is equal to some ai, or maybe bi, over p to the power of ci, where bi, ci are integers. So we allow our exponents to have some denominators, power of p denominator, but there is also an important condition that ei tend to infinity. This is going to be for the most part a technical condition, but what we don't want is to have something like p to 1 minus 1 over p plus p1 minus 1 over p squared plus blah blah blah, where those exponents have some accumulation point below which is finite. Apologies. I have some notifications, so sorry if you hear some buzzing. Yes, so this is the field we will be considering now. So right now it is still complete, but again, it doesn't matter too much for us. The norm is now not discrete because now we'll have p to the power of ei. P is going to have norm p to minus ei. And those numbers do fill in, well, not literally fill in the entire line, but they give that field. Yes, so this is a field of characteristic 0. And this condition, okay, so O of k, if this is our k, O of k is going to be the sums like this, where ei are all greater or equal to 0. Are they? Apologies. Yes, sorry. So I have a screen in front of me right now, so I should be able to see when something is off or not, but sometimes I forget to look at it. Yes, so here I just wrote that those bi and ci are integers. Okay, so now let's see what happens when we take an element like this, modulo p. When we have an element like this modulo p, then we can write that a sum of ai p to ei. This element is actually going to be congruent to the sum of ai p to ei divided by p to the power of p when we consider it modulo p. And this is because of this familiar, hopefully, property that whenever we have p powers and consider them modulo p, then they distribute over addition. So this is, I'm forgetting the name, this is like freshman's dream. So p powers e modulo p behave nicely. Okay. Another example, which is, yes, so I have enslaved this, I've enslaved this dream to give me the result which I wanted. Yes, so thanks to the fact that we are modulo p, we can just expand any element like a p power like this. Okay, and another example is that of f p double bracket t. This is my k now, and O of k. This is going to be fp double bracket t. Okay, so let's verify the properties. Completeness, again, almost by definition. Now, again, the image of the valuation. Oh, I think I forgot to define the valuation on this. So that valuation is defined by this kind of like a t-adic valuation, where t has the norm t to the k has norm c to minus k, where where c is some constant between 0 and 1. For example, we can c to the power of k, not minus k. For example, we can take c to be equal to 1 over p, but the choice of the constant doesn't matter here. Okay, and from this we clearly see that the valuation is not discrete. But I also want to go over this example to illustrate what happens with the first condition when we are in characteristic p. So remember, the third condition says something about what happens when we consider the ring modulo p. But now, in our ring, p is equal to 0. So O of k modulo p is congruent to O of k itself. So this first condition is telling us that O of k itself should have all elements which are p fruits, which are p power. And this means, almost by definition, that k is perfect. So every else has p fruit. And again, to fix that, in characteristic P, there's actually a unique way to fix a ring like that into being perfectoid, namely by taking P fruits of all elements that we have here. But because this ring is nice, it is the same as adjoining just P fruits of T itself. So we can get a perfectoid tree denoted by FP, double bracket, T1 over P infinity. Okay, so those were some examples in characteristic 0 and characteristic P. There are many more examples I could give, but those are the most elementary ones. And to keep the talk accessible, I won't talk about much more. Okay, so now let me say a few things. You may be like a little hand wavy, but motivating things about why the perfectoids are so useful. Namely, the thing is that whenever we have perfectoids, we have a certain operation which is known as tilting. So this is. So tilting is a certain operation which takes a characteristic 0 perfectoid field and produces characteristic P perfectoid field. And at least in the example I have talked about before, the intuition here is that if we have such a sum of AI, P to the power of EI, then what we would like to do is transform this sum or this infinite series into a sum AI T to the power of EI, um, where, where kind of formally P goes to T. So we have a very good question about why those fields are called perfectoid. And you have kind of answered yourself. The answer is related to what I have said here. So if we have ring in characteristic P or field in characteristic P, then the condition for it to be perfectoid is the same as it being perfect, together with this completeness and non-discreteness, which are kind of more of technical conditions. So in characteristic P, being perfectoid is essentially the same as being perfect. And in characteristic 0, we don't really have a good notion of perfectness because there isn't a distinguished prime which would serve the role of the exponent. So what we demand instead is that the ring becomes kind of quote unquote becomes perfect when we consider it modulo P, which means that everything becomes P power there. And this perfectoidness property is actually what eventually lets one consider all those fields, and specifically what lets it be a theory as nice as it is. Because of course we could kind of imagine doing that already to p-adic numbers. I don't think there is a notion of a perfect space such that tilde of perfectoid space is perfect, but it is true for perfectoid fields. So perfectoid fields have perfect tildes. Yeah, in characteristic P, one still calls them perfectoid spaces. Right. Yeah, so yeah, we would like to do something like this. Unfortunately, as I said before, prompted by another question, doing this is not particularly obvious thing to do, especially if you want it to be a transformation which is in any sense a nice one from algebraic point of view. Namely, this thing here. So this thing here, these things here have pretty simple algebra because those are basically polynomials. While for these things here, the algebra is quite a bit more complicated. And in order to make sense of it, we have to do quite a bit more work that's related in full generality into something called bit vector construction. But I will not be getting into that because this is more technical than I would like to make it here. So instead, to actually get this to work, we have to pass to this modulo p word. So modulo p. And then, yeah, we can still consider pretty much the same sum, p to the power of ei. But now, all right, someone is leaving, so thank you very much for joining. Yeah, so here we have those sums. But now, whenever the exponent is greater than 1, greater or equal to 1, then it is basically ignored. And this, again, using Freshman's Dream, makes it so that transformation from P, so that any multiplication or addition, if they were to give some additional multiple of P, then they are just ignored because we are modulo P. So, and here it is actually possible to make a map from P, which takes P to T, or other powers of P to powers of T, to such a thing, AI T to the power of EI. And we can see, so, okay, so this was our field O of K. This is O of K over P. Here, this is some field which we would like to kind of develop from this picture. So I could write an arrow here and say that this is a reduction of this, but of course there will be many rings which have this reduction. So we would like to go in some way in this direction, and this is actually not quite trivial. What we would like to do is kind of stretch this ring into a ring which would have which would allow exponents not just less than or equal to 1, but also of arbitrary degree. And the way to do this is to note that once we have this ring here, we know that this ring here is congruent to Fp adjoint T of those powers modulo T. And again, we can't quite undo this quotient here, but what we can do is note that if we replace T by T to the power of P, then this ring is isomorphic to Fp T1 over P to infinity divided by T to the power of P. I should be taking ideals here. And this is again isomorphic to Fp T to 1 over to infinity over T to P squared, and so on. But now if we forget those isomorphisms, so of course those will be just all the rings we have constructed from this one. then we actually have some other maps from them, namely the reduction map. So if we have something modulo t to the power of p, we can reduce it modulo p. And if we have something modulo t to p squared, then we can consider it modulo t to the power of p and then modulo t. Oh yeah, sorry. So this is sideways. This is sideways isomorphism. And now we have this tower, like downwards going tower of rings with those maps. And the way we can combine them into one thing is using something called the inverse limit. I won't get into, no, not directly inverse limit, because we have maps going, we are taking the limit in the direction opposite to the one in which the arrows are pointing. So this is going to be the inverse limit, which I am not going to define precisely, but this is going to give us, in this case, precisely fp, join all those powers of t. It should not be called direct limit because it goes in the wrong way. If we had a limit going in the direction of arrows, this would be direct limit, but this is inverse limit. This is going to sound very weird on the recording because I will be just arguing with myself. Okay. Anyway, more formally, what we would do is, in greater generality, we would take this ring here, and we would take its inverse limit under the Frobenius map. So the way this here looks particularly nicely because of the shape this ring has, but we can also consider somewhat similar construction for arbitrary ring, and in this way, we construct what I will denote by a OK flat, and this is called the tilt of OK. And then once we have a tilt of OK, we define tilt of K to be K flat, which is the fraction field of O of K flat. And there we have it. From this construction of from this original characteristic zero field, we have developed a construction of a characteristic P field. And this construction has many very nice properties from a categorical point of view and many other points of view. In particular, I will mention a few, most of them mostly informally. But basically, this construction is functorial. This construction is functorial, which in particular means that if L over K extension of perfectoid fields give rise to L flat over K flat extension of perfectoid fields. Yes, so taking the field of fractions commutes with tilting by definition. So we define the tilt of the field itself as the fraction field of the tilt of the ring of integers. We kind of have to do that because if we try to take the entire field modulo p, then we wouldn't get anything interesting because dividing by p kills everything in the field if p is non-zero. Okay. Yeah, so extension of perfectoid field gives an extension of perfectoid field by tilting. Much more non-trivially, it actually works in the other direction. So we have something called tilting equivalence, namely that L of k to L flat of k, L flat over k flat, is an equivalence of categories, which at the most basic level means that this induces that every field extension, maybe I should mention of what categories of extensions of k and extensions of k flat. So this means that every extension of k flat comes in a unique way from an extension of k, of a perfectoid field extension of k. And this tilting equivalence, yes, this category depends on k. If we do not fix k, so this is a conversation we had a while before, we actually do not get quite an equivalence. So because it turns out that there can be many perfectoid fields which have the same tilt. But once we fix a tilt and a field which goes to this tilt, then everything above those two fields is actually going to be equivalent. We aren't going to have any ambiguity anymore. This tilting equivalence actually generalizes quite greatly, namely to something called perfectoid rings or perfectoid algebras over a field, and to even perfectoid spaces over those fields. Unfortunately, I am trying to keep this talk simple, so I am not going to get into too much details for that. And instead, I am going to give some very broad overview of how this entire tilting equivalence business can be used to transfer results from characteristic P to characteristic 0. I'm not even going to do this based on an example, just kind of like a very sketchy explanation. I think I'll go to a new page for this. Okay. So one thing I should say is that perfectoid fields are nice in their own way, in many of their own ways. But if we, in practice, whenever we are doing, say, number theory or whatever else, we aren't going to be stumbling upon perfectoid fields all day long. Perfectoid fields are a very new addition to the theory. So if they were that commonplace, they would have been invented long ago, I imagine. Instead, we live in a boring world where usually we have things over QP, for instance, or over FP without all those fancy additions. So we have stuff over QP and stuff over, say, this FP bracket T. There are a lot of analogies between those fields, so there isn't quite literally a tilting equivalence between them, which would let us directly transfer results from here to here. But there are still many things which are analogous between them. In particular, whenever we have some statement over QP, which say we care about because it came about from considering some étale cohomology of some field, there's a very good chance that there's an analogous statement for stuff over FP double bracket T. And there's a better than zero chance that this stuff over FP double bracket T is going to be simpler to deal with stuff over QP. And there are many reasons why that is. The basic one is that, as I have already mentioned at least twice, the algebraic structure of this field, FP double bracket T, is much simpler. It is a characteristic P field. And also, because it is essentially a field of polynomials, we also have some nice things like derivatives. So if we have, and the derivative is an immensely useful tool whenever we are doing algebra over some structure like this, because it lets us take some relations and then generate more relations from them. And there is no analog of that from QP. So suppose we have some conjecture over QP about stuff. And then we state analogous conjecture over FP double bracket T. And suppose it becomes a theorem. So now we are happy because we have a nice statement about FP double bracket T. But of course, the original statement was about QP, and we would like to get some stuff about QP, which is here. So there, and we would like to use this new machinery of perfectoid fields to achieve that. So what one may try to do is take this stuff and somehow modify it into stuff over a perfectoid ring or a perfectoid field. So say if we had some variety over QP, then we would like to construct some variety over a perfectoid field like this. And then call this perfectoid field K. For example, K may be QP, this P1 over P infinity. And then, since we are now over a perfectoid field, then we have this bridge, which gives us stuff over a perfectoid field. K flat. And now once we are over this K flat, which in this case would be Fp double bracket T1 over P to infinity, we can actually take this theorem and apply it to stuff over this new perfectoid field. And because all this perfectoid tilting business is very nice, it turns out that this theorem can actually go along this way. And in some special cases, it can even go back to this stuff over the original field. And therefore, the theorem originally over Fp bracket T now becomes a theorem. So of course, this all sounds very nice, but is there any reality to it? Well, you can imagine that if there wasn't, I wouldn't be talking about it. And in fact, there is. And this is actually how, this is actually the original motivation for introducing perfectoid fields and perfectoid spaces by Scholze, namely transferring such results. And he did it with one particular result in mind, namely something called weight monodromy conjecture, which don't ask me to explain it because I don't understand it myself. But this is a certain statement about étale cohomology of varieties over QP, whose analog was proven by Deligny over FP double bracket T in, I don't know, like probably 70s or something. And unfortunately, in general, the difficult part in making this whole diagram kind of work is this first step here, because there isn't a factorial way to take a variety over QP and generate from it a perfectoid space over a perfectoid field. In some special cases there is, for example, if the variety is a projective space or something nicely embedded in projective space. And then we also have that the entire tilting business works very nice with étale cohomology due to something called the almost purity theorem, originally by Foltings, generalized by Scholze. And once we have that, this this side of the diagram is easy. You can easily transfer results about ethyl cohomology here. And then in the special case, if you can generate this perfectoid space attached to a variety, then you can generalize, then you can extend this theorem about ethyl cohomology in those special cases to varieties over QP. Okay, unfortunately, I would love to go into more detail, but I am aware that people here do not have that much background in ethyl cohomology and many other things. So I hope you are satisfied with that. This very hand wavy considerations of how perfectoid fields work. And yeah, thank you very much for attending the talk in that case. This is it. Now you know what perfectoid fields are. Ah, so we have a question. So is this an active field of research today? Uh, this is, I would say, one of the most active areas of research in mathematics right now. So this is still some very fresh theory. This was so perfectoid spaces were introduced by Scholze in 2011, which is less than a decade ago. And year to year, we are discovering new applications of this whole theory. So unfortunately, this with just perfectoid fields, there's only so much that you can do. But once you generate the theory of perfectoid spaces, this stuff over a perfectoid field, then there is quite a lot going on. There is a survey article in which Scholze goes over just a few of the applications of this topic, and I think that article is from 2014. So you can imagine if in 3 years there was so much discovered, then what must have happened in the next 6 years. There is a lot going on about perfectoid fields. There's a lot that can be said there. Are there other finite characteristic fields other than QP for which this kind of thing is used often? So first of all, QP is a field of characteristic 0. So I suppose you can mean more generally any kind of perfectoid fields over which we could work here. I would say not to my knowledge. So you need to, whenever you are forced to kind of use a single base field, I think you're almost always going to use a QP, or rather when you go to actually perfectoid stuff, you'll either use this field with adjoining roots of P, but more commonly you take K in which you adjoin roots of unity. So you take zeta P infinity, where zeta P to the K is primitive root of unity. However, so the reasons why you need such a general theory for perfectoid fields is that, let me try to draw a little blob which looks like a perfectoid space. So whenever you have a perfectoid space, this is not what perfectoid spaces look like. Perfectoid spaces are not potatoes. Whenever you have a perfectoid space, say attached to some ring R, so this is perfectoid ring, each of the points of this perfectoid space, you can attach to it a perfectoid ring, perfectoid field, I mean. This is analogous to a residue field from algebraic geometry, if you're familiar with that. Divide and somewhat more precisely, those fields kind of classify all the embeddings of the ring R, or not necessarily embeddings, just maps from R to some perfectoid field K. And even if you started with a very nice perfectoid space just over this field, some of those residue fields are going to be quite a bit larger, and you kind of have to account for that. Uh, so even though you're only starting with pretty tame fields, you have to face your fears and deal with quite a bit larger fields anyway, pretty soon. Yeah, I agree. It looks kind of more like a peanut. Um, so, but perfectoid spaces are not peanuts either. Okay. We have another question. Can you explain a statement you wrote on page 2 about okay, P isomorphic to okay, K is perfect. Yes, so if we have some field K, say K is a field of characteristic P, and say with valuation, then O of K over P is isomorphic to just O of K, because dividing by P has no effect. And and from this it follows that K is perfectoid if and only if K is perfect. Again, in the light of those other technical assumptions, that is complete and non-discrete. K is perfect, i.e. X goes to X, the P is bijective. This is what it means for a field to be perfect. Okay, I hope that answers the question. Yeah. Do you have any other questions? If not, then I will be stopping the recording. And again, thank you very much for sticking around.